Meanwhile, let's look at some methods for imaging domains. As usual, a table of contents, and then we just go through all these examples. So, one method to image domains, a very historic one, is surface etching. So here the idea is that, especially in ferroelectrics, different domains have different orientations, polarization up or down, and in a ferroelectric, then it would mean that the surface looks different than the bottom. And the top surface looks different from the bottom. Ions are displaced, maybe up, and that means that the top surface, certain ions are closer to the surface than at the bottom surface. And chemical processes can make use of that, and if you put etching agent on the surface, for example, of a ferroelectric, in this case barium titanate, here yttrium-manganite, then the etching is different for the two domain states, simply because the etching agent sees different surfaces with a different distribution of ions. So that's a very, it's a destructive method for doing this, and once you have done it once, you cannot do it another time. If you change your domain pattern, then you would first have to polish to create a neutral flat surface, and then you can do the etching again. So that's not very convenient, but it was one. It's a method that works. Actually, this is something that we did a few years ago unintentionally when we polished our sample, and then we found that the polishing process is also etching material away, so we could see the domain structure just from little steps in the surface. Okay, then surface agent techniques. So that means that you put stuff on your material, like iron powder on a ferromagnetic, and then the iron powder, then you knock the sample a little bit, and whatever you put on top arranges itself. And then you find that it likes to go to one domain and not the other domain, for example, or it likes to go to the domain walls because those are little inhomogeneities. So in an antiferromagnet, for example, it could go to the domain walls because then iron powder, because then there is a little bit of local magnetization. So here you have different examples. Here it's dipolar material that images ferroelectric domains, and here it's ferromagnetic material where ferromagnetic particles image the distribution of those. So surface agent techniques. Well, here it's all, you can also use vapor condensation. So inaccuracy, so if you have an oversaturated atmosphere, then certain inaccuracies attract condensation, then you can see the distribution of domains from that. So there are several ways to do this. Again, it's not very convenient, and still is of a historic value basically. The name for this for ferromagnets is called beta technique. Okay, then I already mentioned the polarized neutron or neutron diffraction, because neutrons can directly interact with spins. And if you work with polarized neutrons, it gets even more selective. And here's this example again that I showed earlier on. So the manganese fluoride domains that were imaged by scanning a neutron beam. And again, as in the optical experiment I showed earlier, with the contrast reversal, depending on the neutron polarization. You can see dark white or white dark. And it's this relatively impractical way of doing it because it takes long and the resolution is still not very good. X-ray diffraction can do it. So not normally, because photons do not directly interact with spins. But you can have spin-dependent electronic bands in your material that create absorption, and that's something that X-rays can see. So then you can image throughout a hysteresis of a ferromagnetic film. I think this is a ferromagnetic film. Gadolinium iron alloy. You can see how the domains are distributed with spatial resolution and then associated with a point on your hysteresis. Advantage is that X-rays have a very high resolution. 30 nanometers is pretty good. And disadvantage is it only sees a very thin layer of material or a thin film. And surfaces, sometimes they are different from the bulk. They're easily polluted, and then this technique is therefore quite sensitive to the environmental conditions. Electron microscopy, that can nicely see magnetic domains, because electrons are influenced in their path by magnetization through the Lorentz force. That means when electrons, as a wavefront, go through a ferromagnetic material, then one magnetization direction would deviate the beams, the electrons in one direction, and the opposite magnetization would deviate them in the opposite direction. And then you see that then you get regions between the domains, so that the domain walls that don't get any electrons, well, twice the number, and then you can see the domain walls based on these deflections. But that's not the only way of doing it. So this is an unfocused way. You get then different brightness at the domain walls, and therefore see your domain pattern. But there's also a way to see the domains directly if you focus your electron beam, which you can do with electric field lenses, kind of. Then it's the principle that is shown down here. So we have the deflection of the electron beam in the two different domains for the two different domain states. And then you put a lens there, an electron lens, and that focuses all the, say, plus m electrons onto one spot, and it focuses all the minus m electrons on one spot. And if you put an aperture here that blocks, say, all the minus m related electrons, you only see the plus m related electrons, then you can really get the brightness between different domains, like dark, bright, dark, bright, dark, bright. That is if you work with focused electron beams. So this particular method is called Foucault method, and there are several other ways to do this. So in this case, lanthanum gallium manganide, some material where you see that the focused electrons, you do not only see the domain walls, but we see the domains. Again, high resolution, but only for thin films or surfaces, because otherwise your electrons get stuck, or they don't even reach the inside. Yeah, a very, very powerful technique is atomic force microscopy. And many of you, or several of you, will most likely work with that during your master thesis, because many groups in our department make use of that. So what you basically have is a very fine tip, almost atomically sharp at the tip end. And that tip interacts with the surface of your material. You see an electron microscopy picture of such a tip. It interacts with your material. So, for example, if your tip is attracted or rejected, repelled from the surface, what happens in response is that the lever on which the tip sits is going to be deflected or attracted. So either if you have attraction, then it goes down, the tip is attracted to the surface. If it's repelled, then the lever goes up. How do you see that? The lever moves because you send a laser beam onto the lever, it's reflected onto some diode, the other way around. Laser beam, diode, and then wherever the spot ends tells you if the lever on which the tip sits is moved in one or the other direction. So you can measure the interaction of the tip, between the tip and the surface, through the deformation of that lever, which is detected by this laser reflection experiment. And that's quite effective because it's a very sharp potential that detects that determines the interaction between the surface and the tip. So if it's atomic force microscopy, you have the Lennard-Jones potential, so when the tip comes closer to the surface, at some point it will be attracted. And then what you could basically say is when it hits the surface, then it's very strongly repelled. So it cannot really penetrate, so if you try to force your tip into the material, it feels very strong atomic forces, and then suddenly it will not really go in that direction. So there is this narrow potential of maximum attraction, and the entire thing then is called Lennard-Jones potential. So then you can have two modes. Either you are always in contact, so then you would move your tip across the surface and try to always keep the same deflection of your lever. So then you can assume if you always keep the same deflection, say here's my tip, now it's here's my tip, now it's attracted, like this, then you move, then at this point it would go up, because this table ends. So what do? You move your tips until you have the same deflection. So it goes up, then controller, down, 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 then it's attracted again, now by the ejector surface. So now there's a very strong rejection, so then again your tip is moved up until you have the same deflection again, and so you can step by step scan the surface. The other way is you always keep the same force, so then you hover, and then it's so constant damping. Yeah, so then you detect the interaction with the surface, not really the contact, but now it's again attracted, you move, detection, the force goes down, so then you go closer to the surface, force comes again, so the force gets stronger, so you move up, and then. So these two modes are called contact mode and non-contact mode. Here you feel the repulsive Pauli forces, so that branch basically, and here the attractive van der Waals forces, so that's basically what you work here. And depending on what you want, you can use one or the other mode. And to do that, then here you see nicely the atomic terraces, the atomic steps on the surface of the strontium titanate. So it's atomically sharp in the vertical direction. In the lateral direction, you have something like down to 30 nanometers. So 30 nanometers in the plane, downwards is super sensitive, picometers. So basically, nuclear, atomic nucleus dimensions are measured. So the thing is that this is not the only mode, so you can play this in many different varieties. So I just described the principle of atomic force microscopy, but you could also then say your tip doesn't measure the reflection here or the deflection of the lever, but what you instead measure is the current, the electrical current going through the tip. Then spot by spot it would measure the conductance of your samples. Then you have something called conductance atomic force microscopy. You can work, I will show this in a minute, with piezo. You can also magnetize your tip, and then the attraction by the surface is not any van der Waals force, but then it's a magnetic field of the surface that you measure. And you have magnetic force microscopy, and so forth. So in the end, we have now about 40 different modes that have been created. So you see how versatile all this is. And depending on what you want, you can use one or the other. So here where you would use a magnetic tip, here you would use a conducting tip, and so forth. So for possibly the most, aside from atomic force microscopy, the most oftenly used mode is piezo response force microscopy. So what happens here is the following. You apply a voltage between your tip and the surface. Voltage between the tip and your surface. So what happens? The voltage, if it's a piezomagnetic material, piezoelectric material, it deforms your material locally. So either that's the piezoelectric effect, you make your material longer or shorter. So by the voltage, you then buckle your material or you create a dent, and that is then what you measure in the atomic force microscopy mode. So it's a little bit like this. So first I apply the voltage, and that is what then the surface does. And that bump that I created with my voltage, that is then what is measured in the atomic force microscopy mode. The other way around would be to poke into it. So it's atomic force microscopy based on the piezoelectric effect, so piezo response force microscopy, or in short, PFM. That's very useful to measure ferroelectric domain distributions, because they are all, remember, ferroelectrics are all piezoelectric. And then you can very nicely, for example, scan the distribution of plus-minus polarized domains on the surface of a lithium niobate crystal. And in this particular example, they showed, okay, here they form bubbles, here they form hexagons. On the bottom, hexagons, and on the top, bubbles. Yeah, so this kind of stuff you can do. It's very powerful. So this big pattern was recorded using piezo response force microscopy. It's a ferroelectric yttermanganite sample. I showed the material a number of times, and I'm showing it here because first of all it's a nice picture. It's really high quality, as you see, and look at the resolution. Much better than optics, for example, and in any case way better than neutrons. And then you have these plus and minus polarized regions showing up as bright and dark areas. What is a bit unusual about this pattern, and this is also a little sidetrack why I'm showing that. If you look at that, you would say this is not like cow patches, so like distribution curly domains that are distributed in some form, but something is odd here. Although at first you may not easily see what it is. If you stare at this long enough, in the end you will find you always have meeting points of 6 domains. Bright, dark, bright, dark, bright, dark. So always 6 of these meet in one point. Wherever you go, there's no exception. Always 6 meeting in a point. So there are reasons for that, mathematical reasons. So this is a topologically created domain pattern. So the reason is that domains are not only ferroelectric domains, they're also elastic domains, so distortive domains. Here the ferroelectricity is improper. What it primarily is, it's deformed in some form, and then in 6 different ways, so 6 distortive domain states, and 3 of them are plus polarized and 3 of them are minus polarized, improperly ferroelectric. And then this is what you see in the picture. So the plus, minus, plus, minus, plus, minus distribution of the polarization, which in fact reflects 6 different distortive domain states. So this one is then different from that one. This bright one is different from that bright one. But since you only see polarization, you only see the minus out of these 2 labels. So stuff like that happens, and then can produce very beautiful patterns actually. So this is one that we measured on a sample. Same idea, right? So 6 meeting in one point, always. In principle, this is a bad sample, so meaning it's not as homogeneous as this one. This happens typically when you grow your sample and then you just look at it without any further treatment. And then this reflects growth inhomogeneity. So possibly here solidification happened first, and then to the outside material was added when it crystallized. And then you see little strain effects and so forth. But you always have this 6-point meeting effect, only here it shows you certain gradient in domain size. But that can be very beautiful, as you see. Huh? Yeah, here is a little excursion further into it. I mean, this is just to tell you that very often there's much more out there than just saying, okay, I'm looking at ferroelectric domains. So when you have these meeting points of domains at the surface, then you have a spot here, where they all meet. And if you go into the material, into the bulk of the material, the spot will become a line, right? So here we see this computer simulation of these 6 domain states, those. So 3 plus, 3 minus polarized, but here it actually then shows the 6 distortive domain states, and here you see these meeting points again. 1, 2, 3, 4, 5, 6. Okay, now let's make the cube transparent. So what do you get? The meeting point into the sample, there are lines. So watch at this spot. It's now the beginning of a line, and that's how this spot moves into the sample. You get this box full of noodles, and you see that these form circles all the time. So these are designed to be little loops. And then you make it intransparent again, and this line end now becomes one of these meeting points again. 6 domains. Yeah?
But I didn't understand what these lines represent.
The meeting point of the 6 domains.
Ah, okay.
Yeah, and then of course, what is a spot on the surface is a line into the material.
Yeah.
So if you plot these lines, then this looks like that. This is one of the frames that I just showed. And then you would say, okay, fine, it's a box full of noodles. Now, not exactly, because noodles, they don't form loops. They need to form loops, and also if you think about the domain configuration, what is not possible is this kind of loop. That's not possible. So they are all separate loops that meander through your material. The only point where they are not loops is when they are cut by the surface. Then if the crystal continued, it would be a loop. Okay, still, why am I showing you that? Because if you now go to cosmology, completely different field, that's what people say could be this distribution of strings that formed in the universe after it cooled down after the Big Bang. You would say, wow, this is really something completely different. But cosmologists, they calculate these things and they say, yeah, the universe went through certain phase transitions, like ferroelectric goes through a phase transition when it solidifies, when it forms its domains. And the same mathematical rules are at play. So in principle, this could be seen as a model for the universe when it cools down, And then you cannot replay the Big Bang, but what you can do is you can work with this crystal. So you can study certain scaling relations that would apply to strings, cosmic strings. You could study on such a ferroelectric material. Suddenly you have a really big connection from condensed matter physics or material science to cosmology. And why this works is because the same mathematical rules are at play, and this is when I say topology. So topology are certain mathematical criteria that lead to certain patterns. And the same topology is at play in this and in that case. That's typical that in very different areas you find the same mathematical laws. You can see the same, okay, anyway. So there is a paper that makes use of that and verifies certain scaling laws that were predicted for the post-Big Bang universe on this crystal. That's the paper. So you see, very often there's much more to that. It can be very abstract, but it's interesting to keep it in mind. Good, that is another ferroelectric domain pattern that actually we measured just, so the previous one, the nice one that I showed before on this one. So this one, and also that one, we measured in our lab, not for the science, but we wanted to test our piezo response force microscope. And then we did this, and then we said, oh wow, this looks beautiful. So that's what you get when you look at strong langenite films, which are also being ferroelectric. Strain-inducible strain of the film makes it ferroelectric, and then you have very small domains, 20 nanometer size, in a mode called electrostatic force microscopy. So you probe charges on the surface, basically. And then you see this beautiful pattern, and so you can see, aside from the usefulness, they really form, they can have an aesthetic value. When I saw this, I thought, oh wow, this reminds me of something, maybe this. So those of you who still watch Star Trek, that is actually not the Borg cube, this is our domain pattern that I've just shown. Good. Then polarized light, so now we are going to optics. Polarized light microscopy is also a way to see domain patterns. Remember the early example of the nickel oxide? So this strain distribution that reflects the antiferromagnetic pattern was measured with optical techniques. So you send in a polarized light beam, polarization gets distorted by the birefringence of the domains, and then you can image that. Here you see a different material. Again, there's no real reason to show it besides that it's about the most complicated type of domain arrangement, so nickel, iodine, boroside. And if you look at that, if you look at the order, it's ferromagnetic, ferroelectric, ferroelastic, and ferrotoroid. So all of those four primary ferroic orders in one material. So in that sense, rather spectacular. There's something that nature does, even though this is not necessarily, I mean, you cannot really see, so the signal from all these domains, the birefringence adds up, and then you get a colorful pattern. So you don't really see the domains. But at least you see the non-uniformity of the brightness distribution, and that tells you that there are domains inside. So that's linear birefringence typically, or you can also work with circular birefringence, strain-induced birefringence. So basically, it's optics means that you change the polarization of your light and you detect this with a polarization microscope. So So the resolution then naturally is 1 micrometer because that's the wavelength of light. And it's non-invasive, cheap, whatever else. The optics is really convenient. Now, how do you see magnetism and the distribution of magnetization in a sample? Then the D technique that is mostly applied is the magneto-optical Kerr effect. So you again take polarized light, you reflect it on a magnetized sample, and then the polarization of the light is rotated by the magnetization. And the nice thing is that if it's plus magnetization or south pole or whatever, plus magnetization, you get plus rotation in your angle, and if it's minus magnetization, it's minus rotation. So you can nicely image plus and minus magnetized regions on the sample with that. Very convenient. Again, 1 micrometer resolution. You just need the light source and then a polarization in the microscope, and then you see your domain distributions magnetically. Very nice, very convenient. Here you see nickel. This picture you have also seen before, and then how the different brightness from this polarization microscopy experiment converts into magnetization directions is shown here. Good. Then, now comes something that is a bit more special, but still powerful, and that's one of these things where I always say this is what you get here at ETH in this department, and not so much elsewhere. And that's the use of nonlinear optics to describe domain patterns, to show domain patterns. So when you think about domains, and in the previous example that I've shown, that you want to resolve something, and resolving something spatially, you possibly immediately think of optical techniques, microscopy, spatially resolved things. And we also talk about imaging ferroic structures. Ferroic, as we now know, means that some symmetry is broken. So we need an optical technique that is very sensitive to symmetry breaking. And that brings us to so-called nonlinear optics. So what is nonlinear optics? It means, you have already seen the example with a periodically poled lithium niobate, frequency converting optics. So normally you have some electric field, you get a polarization. And it doesn't really matter if this is a static field or oscillating in omega, electric field polarization. But for very strong fields, you can also get not only electric field proportional, but also coupling to the square or to the cube of the electric field. So let's now take this first term here and write it down. So we have two electric fields on the ingoing side and the polarization on the outgoing side. Since these oscillate, it's light at omega, two of those give you 2 omega. That means this term is exactly that kind of frequency doubling that I showed before. You could also say 2 electrons are absorbed, no, 2 photons are absorbed simultaneously, kick the electrons up here, and then the state relaxes by the emission of a single photon, and then necessarily has to have twice the energy, twice the frequency. Right? No? This is called nonlinear optics because it goes away from the linear contributions that you see here, to higher order ones that are then called nonlinear. Typically you need lasers for doing that because it's a weak process. So how do you compensate for that? You make very strong electric fields, so like laser fields. Good. That's then how it works. You take a laser. This is the very earliest concept of a laser. Very coherent, very intense emission, very controlled, and then excites your electrons so effectively that you see these contributions. So here is a typical lab for doing this. So here you have the big laser. That's all laser. And then here in the end, in the back, you have your setup with your crystals and samples where you do this frequency doubling. That's actually what we would see on our lab tour that we at least at the moment plan to do sometime in November. Yeah, so you can have then a huge wavelength range to do this. Now it's even bigger than this. And you have this resolution that is only limited by optical wavelengths. You can do it in a big lab like this, but you can also do it in a microscope like here. So you send laser light, possibly going in through some fiber into your microscope, and then it goes through the microscope, is focused on the sample, light is reflected back and then kicked out by this dichroic mirror, and then you detect it in some sensor. Different modes to do this that I'm not going to discuss in detail here because it goes a little bit too far in any case. That's how you detect these frequency double contributions. Good. Now, who discovered basically this frequency doubling process? That is shown here. So Maria Goeppert-Meyer. And she did it in theory. So in the, what was it, 20s sometime? 31. Okay. 1931, she said there should be these processes that I've just shown. Those ones. So she said these two quantum jumps, they should exist. So she did this in 1931. Then published a paper. In those days, you would still do it in German. And this is one of these cases where the idea was there, but not the technology to realize it. So she exactly knew that you can have elementary acts with two quantum jumps, but you would need very intense light sources to actually. She thought about atom optics, but even if you do it in, she talks about light sources. So you would need a very strong light source, and then you can see that. But in those days, you didn't have lasers yet. So it was a theory work, and right after the laser was invented, it was actually then demonstrated experimentally. So here's the experiment that you have seen before, 1961. So this is barely 3 years after the landmark paper on lasers. People demonstrated that in quartz, you can generate optical harmonics. So in this case, frequency doubling, sending in light at 700 nanometers and getting our light at 350 nanometers. And this is something that you have sometimes. It's the same with airplanes. People exactly knew how to build airplanes. So what limited the demonstration that you can really fly? They needed strong enough motors. Once they had it, the plane was immediately there. Same here. They exactly knew that these things could exist. They needed a strong light source for that. Laser was invented and it was done right away. What is interesting about this publication, which is then in that sense really historic, if you look closely, that's where your frequency double data spot should show up, right? And if you look closely and even more closely, then there's nothing. So what happened? In those days, no computers, no PowerPoint, no Photoshop, so you would send in chemical slides, film. They exposed this on film. Send it to the editor, and editor said, okay, very nice, we'll publish this. But first we need to remove all the dust speckles from this film. So they removed all the dust speckles, including the data point. I've once seen a picture of the actual chemical film, and yes, there's a point, it's even slightly brighter. But yeah, so they never made it into publication, and they never even corrected that. So because everyone could go to the lab and verify that this worked. So there's no erratum published on this one. It's a nice, one of these anecdotes that you have in science. Good, but going back to Maria Goeppert-Meyer, so who predicted that in theory in the 30s? When you had a paper, you would have a so-called reprint, where you just have the paper, not the entire magazine, but you would only have that article separately published. I still have tons of that in my office. Now you don't need it anymore because everything's online. And this one was then sold at Christie's for $2,000 to $3,000. So you see, this is why I keep my reprints. One day I can sell them. Okay, why is there a clicker question on this one? Because she got a Nobel Prize for things like this. So, a question to you. Nobel Prize in Physics. So how many of the 229 Nobel laureates in physics so far were women? And that's the range. So, should say 229 up there, because I just forgot to adjust it to this here. But 121 to 229 is the correct question. And that is what you should tell me what you think. How many were there? How many women so far got a Nobel Prize in physics? This basically means all of them. That's the intention, so this should be 229. Everyone has a strong opinion on this because now we are already at 23. Good, so 27, this I think is almost everyone knows it. So who knows? Tell me names. So who won, which women won the Nobel Prize in Physics? Curie, yes. Maria Goeppert-Mayer, because I just mentioned. Who else? Okay, let's have a look. Yeah, Shane, huh? So it's 0 to 5, 5 exactly now. With this year it's now 5. So there was a time of more than 100 years when only one woman won it, and that was Maria Goeppert-Mayer. So there was Curie sometime around before 1910. Then Maria Goeppert-Mayer in the 50s, and then nothing until 2018, when suddenly someone realized that this is simply not possible. And since then, 3 women received it in 18, in 20, and in 23. And that's it. So it's really a shame. So of course you could argue, oh, maybe there were not so many women in physics that could have won it, but there are names like Lise Meitner, who didn't get it. Otto Hahn got one, she didn't. Then there is, what's her name? So she discovered the background radiation in the universe, the 3 Kelvin radiation, was carefully overlooked. Then we have, yeah, it's like that, carefully overlooked, really. Then we have, here. Let me see. So this is Lise Meitner, who didn't get it. This is Chien-Shiung Wu, who discovered the CP violation, so charge parity violation in particle physics that leads to the direct emission of electrons in a very cold decaying material. Something very mysterious. It's a real asymmetry in our universe. She discovered it. She didn't get the Nobel Prize for that. Vera Rubin, I don't exactly know what she did. But there are societies named after her, so I don't even remember. Sorry. Lena Hau, and then here we have Jocelyn Bell Burnell. She was the one who co-discovered the background radiation in the universe, also carefully overlooked. Yeah. So now it's getting better. People are waking up, but still, it's a shame. So next question. So 2 thicker questions in the wall. Somehow I ask questions. Yeah, so now let's look at Switzerland. So, this twice a year, the Swiss National Science Foundation, SNSF, distributes funding for research project applications. How about the success rate in this? So, who heard about the Swiss National Science Foundation? Yeah, so if you stay in science, it will become super important because they give you the national money, the federal money. So how about this one? So how was the success rate in this? Higher for female applicants, higher for male applicants, equal for both? Go ahead. It's not. It's working. No. Okay, go ahead. So if you stay in science, the dates 1st of April and 1st of October will be burned into your memory because this is when these are the deadlines for the submission. So, let's say 15 seconds. So let's see. Yeah, I guess you were a bit biased by the previous clicker question, but in fact, it's equal. So, I mean, this one, it's even slightly higher for female applicants, but it's within statistical variations. I think it's like 51 or 49 or something like that. I mean, success rate, not numbers, because there are still less women in science than there are men, but I asked about success rate. So, that's great, actually. So, because usually you will always go for the prejudiced one, but in fact it's not by intention, so it just comes out like that. So now people, at least in this respect, people really look at the scientific quality and nothing else. But that doesn't mean that everything is good. Okay, so much about that. That was a little sidetrack. Oh, 9:30? Let's go into break.
Not if somebody's
Ja, aber ich habe alles verletzt. Probieren. Aber du musst auch. Die Labbe ist
Look, ich kann dich protecten, aber morgen ist schön.
Ja, ich freue mich mega.
Typically they all I mean, it can be very small.
Ja, eher schlecht. Kann man meinen, Zeit
mit Cortison.
Ausgeschöpft viel
You mean for the frequency? Yes, too.
Morgen, ja.